Alright, so for this problem, another rolling with and then without slipping problem, um, we're going to approach it in a little bit less calculus-oriented of a way that might be a little bit easier. So hopefully that'll kind of help, rather than sort of mixing up explanations from previous questions. I decided to do the other one kind of the calculus way and this one the sort of less calculus way. So, alright. Here, we're not being told quite as much in terms of what to use with Newton's laws or anything like that. But all we need to do is we need to derive with an expression that is the velocity as a function of time. And so if we draw our free body diagram, then after the cue ball is finished hitting it, there's only three forces still, right? There's the normal force, there's the weight, and there's friction, right? And roughly those are all drawn at their points of application. So the linear velocity of the ball changes, right, because of F equals ma, and we have one linear force, the force of friction, and the force of friction is just mu k mg, right, because the normal force and the weight are equal. And so this tells us that the acceleration is mu kg. That's a constant acceleration. So because we have a constant acceleration, we can use a kinematics equation. So v equals v naught plus at. So now the only thing to note is this acceleration is negative, right, because it's in the opposite direction of our positive velocity. So v is v naught minus mu k g t, right? And this is the velocity as a function of time. That's it. Right, since we didn't need to write the differential equation, we don't need to worry about any of that. This will work as well in the other, in the more recent problem. But since you had to set up the differential equation, you wouldn't be able to get the points for that. Okay, so that is part A, and that's 4 of the 15 points. So part B, now we have to do something about rotation. So we're going to use rotational version of Newton's law. Tau equals I alpha. And again, the only force that causes a torque is friction. So this is mu k mg, and we're told the thing is radius r. This one is a solid sphere, so it has a different moment of inertia, but it's pretty similar. Right? So we're going to cancel some r and m terms, and we're going to get that alpha is 5 mu k, not mu g, mu kg over 2r. Right? And similarly, this is once again, everything over there is a constant, so alpha must be constant. So that means we can use a kinematics equation for that. So omega equals omega naught plus alpha t. And so here, omega naught, it's not rolling at first, or not, yeah, it's not rotating at all at first, so that's 0. And the angular acceleration is a positive one because it's causing it to start speeding up. So this gives us, right, omega equals 5 mu k g all over 2r times t, right? And that's it. So once again, you can see the key is starting with Newton's laws. And then because we have constant accelerations and angular accelerations, we can just use kinematics. So that's A and B. B, determine the time at which the ball begins to roll without slipping. So once again, this is when we have the condition V equals omega r. That's the condition that must be true. And we have v of t and omega of t, so we're just going to figure out when those are equal. So that's v naught minus mu gt equals 5 mu, oops, this is mu kg over 2r times t. Right, so the r's will cancel. and we'll get V naught equals mu kg plus 5 halves mu kg. So V naught equals 7 mu kg over 2. Oops, this is all times t, so that's times t. Or we get that t equals 2 V naught over 7 mu kg. Right? So that's the time when the rolling without slipping constraint is first satisfied. All right, so all pretty much the same so far. The tricky part to this one is part D. So we're told that when the ball is struck, it acquires an angular momentum about the fixed point P, right, that's drawn. So this in the original picture, right, is like the point like right here. That's point P, is right at that base. And so even though it's not rotating initially, it has to acquire an angular momentum as the center of mass moves away, right? This is the idea that L equals R cross P. So because it has a linear momentum and there is a distance, right, R, that's a terrible drawing. Right, that's R. So there is an angular momentum of the center of the ball about point P, even though it's not rotating initially. Obviously, it starts rotating, and then it would have it would have angular momentum about its center as well. But it has, regardless of whether it rotates or not, it has an angular momentum across that point using this equation. And so we're then told that even though it acquires angular momentum, the total angular momentum about point P must remain constant despite the fact that there's a frictional force that causes it to rotate. So right, as the ball is over here, right, we have friction, the normal force, and the weight. We're being told that no matter what, the angular momentum remains constant about point P. Right, that's the key, about point P. And so to do this, we need to recognize really what this formula means. This R is the distance between the point of interest. Actually, there's probably an easier way to do this. Let's get rid of that. So we know that if we want to change the angular momentum, we have to have a net torque, right? Right? That's another rewriting of Newton's second law for rotation. So if we can show that the net torque, which is R cross F, is 0, then we show the angular momentum does not change, right? Or the derivative is 0. So the force involved here, right? If we draw, the R here is the distance from P to force application. So point P to the point of the force application is like that line for friction. So for friction, those point in the same direction. So the sign, right, if I write this as RF sine theta. So for friction, that is 0 degrees. So there's no torque due to friction. Right? The other two forces both will have torques about point P. Right? If I draw in blue, right, the normal force and this, that's an angle. But the weight force and this is the same angle, but they're in opposite directions. So the normal force and the weight both exert torques, but they're equal and opposite torques. So if we were to write tau F plus tau N plus tau W, we would get this is 0, and these two equal and opposite. And so that means that this is 0, no matter what. And since this is 0, that tells us that the angular momentum is a constant. Okay? So the key to recognize with this one is that if you can figure out the torque about this, normally we talk about the torque about the center of the object. Here I picked a point P that's not on that object, but the same rules still work, right? This rule, namely. And so from that we can show that there's no net torque. And so then get part D as well.